One of the most popular graph theory algorithms is the Kruskal's algorithm. It's employed to find the minimum spanning tree of a weighted graph. The minimum spanning tree of a graph G is a spanning subgraph of G that is a tree and has the minimum sum of weights. The Kruskal's algorithm starts by sorting edges according to their weight. Then for each edge, if its two incident vertices don't belong to the same tree, it joins the two trees. This process gets repeated until we obtain a single tree that contains all vertices of the graph is the minimum spanning tree. We are not here to discuss the implementation of the algorithm nor its proof, we are just interested by this part. If its two incident vertices don't belong to the same tree, it joins the two trees. What should we use to handle these operations? To accomplish this, we will use a disjoint-set data structure, the one we will talk about today. The disjoint-set data structure, also called union find, maintains a collection of disjoint sets, sets that have no intersection, no common element, and gives the ability to add new sets with the makeSet operation, find the set that a given element belongs to with the find operation, and merge the two sets of two given elements with the union operation. Perfect for Kruskal's algorithm. At the beginning, we add a node for each set. We can check if two nodes belong to the same tree with the find operation, and we can join the two trees of the two incident nodes with the union operation, because each tree is represented by a set whose elements are its nodes. How to implement this data structure? A first straightforward but not efficient solution that we may think of is to simply maintain an array of sets. For adding a set for an element, we just append a new set that contains that element. For initialization with an array of elements, we simply make a set for each element. Initially, each element has its own set. For finding the set an element belongs to, we just traverse the array of sets while checking if the element is in the actual set. We return the index of the one where the condition is true. And to join the sets of two given elements, we first find their sets, and if they're different, we transfer the elements of the second one to the first one, and clear the second one because we don't need it anymore. This implementation works, but as said earlier, it's not efficient. Let's first see the reason. Adding a new set for an element is not a problem, it can be done in O of one time. We're just creating and appending a set of one element. However, for finding the set an element belongs to, we may need to traverse all the sets. And we have n of them. We deduce that this operation is an O of n time. Searching is an O of 1 in average because we're searching in a set. Same result for the union operation. We start by finding the set of the first element, O of n, the set of the second element, O of n, move elements of the second set to the first one, O of n, and clearing the second set, O of n. We get O of n time for union operation, inefficient. The way we implemented union find is definitely not the best way. Let's see something else. A lot of data structures concepts are actually abstract, which allows us to have a variety of possible implementations that can even be eccentric. And the disjoint-set data structure is a perfect example. Even if it's named disjoint-set and actually manages sets, we are not obliged to implement it with sets. Instead, in the implementation we will discuss, each set will be represented with a rooted tree, where the root is the representative node of the set. And each node has a link to its parent, which is necessary for the find operation, to actually be able to move to the parent until finding the root, the representative node of the set. A directed edge from A to B means that A is a child of B. Note that the parent of the root is itself. It will help us know that the actual node is a root. Here is an example. We have these disjoint sets we can represent them with this forest. Each set is represented by a root tree. With this representation, how to perform each one of the make set, find, and union operations. For adding a set, very easy. We just create a node that points to itself, to actually have a new tree of one node that contains the element, which is also the root. For finding the set an element belongs to, we actually want to know the representative of the tree it belongs to. To do so, we keep going to the parent until we find the root, until we found the node whose parent is itself. And for performing the union of sets of two given elements, we found the representative of each set, and we set one of them as the parent of the other one. What happens is that one of the roots doesn't become a root anymore, it becomes a child of the other root, which implies that all its descendants become included in the other set. And this is what we wanted. All elements of the set got moved to the other set just by adding this link between the two roots. We connected them into one big tree, one big set. I know, representing disjoint sets this way can look weird and you may not understand why, but you will see the impact in time complexity analysis. Let's apply these operations on an example from scratch. We have this list of elements. Initially, we make a set for each one of them. In our forest, we make a node for each element, that is considered the root. Now let's apply a bunch of union and find operations and see what happens. First we have the union of B and F, the representative of B is itself, and same thing for F. Last thing, we make B the parent of F. Then the union of F and H, the representative of F is B and the representative of H is itself, and we set B as the parent of H. Then we have find H, we start from H, then its parent is B. The parent of B is itself, so it's the root, we return it, the representative of H is B. Then the union of A and G. A is the root, same thing for G, and we set A as the parent of G. Then the union of F and A. The root of F is B, and the root of A is itself. We set B as the parent of A. Then find G. From G we go to A, from A we go to B, and B is the root. After it we have union of C and D. C is the root, D same thing, we set C as the parent of D. Then union of C and E. C is the root, same thing for E, and we set C as the parent of E. Note that we're by default setting the first root as the parent of the second root. Is it the best way to choose the parent? We'll see that later. Then find E. From E we go to C, and C is the root. Find E returns C. Last operation, union of D and A. Representative of D is C, representative of A is B, and we set C as the parent of B. We included all descendants of B in the set whose C is the root. And we got all the elements in one big set. Let's have a look at the implementation and see if it's efficient. In the initialization, we create a parent hash table where the key is a node and the value is its parent. After it, we make a set for each element. Making a set for the element X is done just by setting X as the parent of itself. Because we don't really need to create nodes and stuff. Nodes are in reality keys of the parent hash table. For finding the root of the tree of a given element X, we recursively keep going up in the tree until we reach the root. In code, if X is the parent of itself, then we're in the base case, it's the root, we return it. Else, we recursively call the function but with its parent. Last operation, union of trees of two given elements. First step, we found the representative of the tree of X and the one of the tree of Y. We can do so by using the find function we just made. And here we have two cases. We have the case where they're equal. It means that they already belong to the same set. We do nothing. We directly return. Else, we have two roots root X and root Y, we set root x as the parent of root y to perform the union, to merge them into one big tree. We're done with the implementation. Let's see if it's efficient. Okay, imagine that we initially have these elements and we perform these operations. Now we want to perform the operation find A. This is what happens. Here, we needed to traverse all the n nodes for finding the root of the set of A. So with this implementation, find operation has an O of n time complexity in the worst case. Same thing for union operation because it uses find. Inefficient implementation again, I guess is the case. We got an inefficient implementation because we made a big mistake in the union operation. Try to find it. The mistake is that when adding a link between roots, we were always setting the first tree as the parent of the second tree, always, regardless of the size and the height of the trees. And this is why you have the case where we get a tree that requires O of n time for the find operation. A better alternative is to perform a comparison between the trees to know which one should become the parent of the other. Two popular properties are the size and the rank. The size is simply the number of nodes of the tree, and in union by size, we compare the size of both trees before deciding which tree becomes the parent of the other. And obviously, the smaller tree gets added to the big one, to avoid increasing the height, because increasing the height of the tree will make the find operation longer. The find operation speed depends on the height of the tree. And if they're equal, we choose anyone to be the parent. In this example, the tree to which 4 belongs has 4 elements, and the tree to which 9 belongs has 5 elements, so the second tree becomes the parent of the first one. Integrating union by size requires adding a few things to our actual implementation. First, our nodes actually have one more attribute, the size. This is why in the initialization, we create a hash table size where the key is a node and the value is its size. When making a new set, initially we have a single node, so the size is 1. We set the size of the new node to 1. And in union operation, we need to add two things, comparing sizes and updating the size of the tree that got bigger. After calculating root x and root y, if they're equal, then x and y are in the same set. Else, we need to merge, so we start by comparing sizes. If the first tree has a smaller size than the second tree becomes the parent of the first one. We assign root y to parent of root x. And we update the size of root y because it became bigger. We add to it the size of root x. It represents the number of new elements that have been added to the second tree. Else is the opposite. We assign root x to parent of root y, and we update size of root x by adding the size of root y to it. What about the rank? The rank is simply the height of the tree, the maximum length of a root to leaf path. We use it to know which tree to set as the parent. Obviously, the shorter tree gets added to the long one, because adding a short tree to a longer one doesn't increase the height, which is what we want. So if the first tree is shorter than the second tree, we add root x to root y and the rank doesn't increase. Else if the second tree is shorter than the first tree, we add root y to root x and the rank doesn't increase. Else if they have an equal rank, we can choose anyone to be the parent. But this time, the rank gets unfortunately increased by 1 because the height of the result tree is greater by 1. Let me show you an example. First of all, the height of a single level tree is 0, not 1. This is why here the first tree has a rank of 1 and the second one has a rank of 2. The first tree is shorter, so we perform the union by adding it to the second tree. As you can see, the rank didn't increase, it's still 2. But if we merge two trees of the same rank, we get a tree with a rank that is higher by 1. The rank increases by 1. It became 3 here. How to implement union by rank? Same as for union by size, we need to add an attribute rank to our nodes. We create a hash table rank. When making a new set, it initially has a single node, and the height of a tree of one node is 0. We set the rank of x to 0. And in union operation, we start by calculating root x and root y. If they're equal, x and y are already in the same set. No union to be done. Else if the rank of root x is smaller than the rank of root y, we need to insert the first tree in the second one. So root y should be the parent of root x. We assign root y to parent of root x and the rank doesn't change. Else if it's the opposite, rank of root x greater than the rank of root y, we assign root x to parent of root y and the rank doesn't change. Else if they have an equal rank, we choose anyone to be the parent, for example root y. Root y becomes the parent of root x. But the rank gets increased by 1. We increment the rank of root y. Remember the example. And we implemented union by rank. But why? Why would we use union by size or union by rank? As you may know, the time required for a find operation is related to the height of the tree, because we go up by one level at a time. And union by size and by rank are here to control the height of the tree, to avoid having trees that are too deep. And by applying union by size or by rank, the height of trees will be in O log n. So for find and union operations, we get a time complexity of O log n, better than O of n. Are we done? Is our implementation efficient enough? No. We still have something else to make it better. Imagine that we have this tree, and we want to perform find A. We need to traverse 5 edges. A bit later, we perform find B. We need to traverse 4 edges. Later, we perform find A. We need to traverse 5 edges. You can see that we're traversing a lot of edges, all that because nodes are not pointing directly to the root of their tree. There are a lot of intermediate nodes that are making find operation longer. To fix this, every time we traverse a bunch of nodes in a find operation and find the representative, we set it as their direct parent, so that in the next find operation, we find it directly, without traversing intermediate nodes again as we do in the first time. Let me show you an example. We want to perform find A, so we start from node A. Its parent is B, we go to it. Its parent is D, we go to it. Its parent is H, we go to it. Its parent is L, we go to it. Its parent is K, we go to it. Its parent is K itself, so we found the root, it's K. And K is the set representative of A. Find A should return K. But not only, K is also the representative of B, D, H, and L. Find operation with all of these nodes should return K. By knowing that, we deduce that it's better to set K as the direct parent of all these nodes. To accomplish that, we traverse nodes backwards while setting K as their parent. Here is what happens. We traversed A, B, D, H, L before finding K. Now we go back the opposite way. We go back to L, we set K as its parent. It's already the case, nothing changes. Then H, we set K as its parent. Then D, we set K as its parent. Then B, same thing. Then A, same thing. Now for next find operations with all these nodes, we will have to traverse one edge only instead of multiple ones. Now try to do the same thing with find V operation. What happens is that from V we go to S, then from S we go to U, then from U we go to K. Then K is the root, we stop. We move backwards now. We go to U. K is already the parent of U, nothing changes. Then we go back to S, we set K as its parent. Then we go back to V and set K as its parent. And the process stops. We don't continue until Z because the process started from V, so recursive calls stop at v. By using this technique, you can see that find operations, and by consequence union operations, will take way less time because paths from nodes to the root become shorter. Basically, it's a cost that we pay once to reduce time needed for next operations. And this technique is called path compression. It's a technique to optimize find and union operations by shortening node to root paths, by eliminating passing from intermediate nodes. It operates by setting the find operation result as the parent of all intermediate nodes it passes from during the find operation. To implement it, we need to modify the find operation only. The find function is recursive, which means that after it traverses nodes, it needs to traverse them again backwards to continue remaining instructions that come after the recursive call. Which is exactly what we want. After finding the root, we want to go back to our node to set it as their parent. In code, if the parent of x is itself, is the root, we directly return it. Else, we recursively call the function with its parent, we grab the result and assign it to the parent of the actual node, as we did in the example. And we return that result for remaining calls. Like, instead of directly returning the result returned by the call, as we were doing before path compression, we'll first assign it to the actual intermediate node, then we return it. By doing so, we implemented path compression. By the way, if you want to know more about recursion and understand techniques like the one we use now, I recommend you to take the Inside Code Recursion course. The link is in the description. Now we learned about union by size or rank and path compression, and by applying these two techniques, we get a very efficient disjoint-set implementation, because the amortized time complexity of one find or union operation becomes O of alpha of n, where alpha of n is the inverse Ackermann function, a very slowly growing function. It's so slowly growing that alpha of n is at most 4 for any practical value of n. This is why operations of this disjoint-set data structure are done in almost constant time. The proof is omitted for this lecture. Now that you know the disjoint-set data structure, you can apply it, for example, in the Kruskal algorithm, or to keep track of connected components of a graph, or to study percolation systems, or to detect a winner in hex game, and many other cases. In the next lecture, we will apply it on the last case we mentioned, detecting a winner in hex game. We've reached the end of this lecture. I hope that you now understand how the disjoint-set data structure works and its implementation. In the description, you will find a Python program where you can perform a bunch of union find operations, then use show method to see the forest result. It uses NetworkX and Matplotlib modules. If you enjoyed this video and want to support the channel, like and subscribe, and you can buy one of the Inside Code courses you will find in the description. See you in the next video.